Welcome back, folks. Here's the next special case for nodal analysis. We've got a voltage supply, but now this voltage supply is not connected to ground. And this creates a little bit of a problem, not a problem that's insurmountable. We can still use our fundamental theorems of circuit analysis, or laws of circuit analysis, to make this happen. So let's take a look at it. There it is. Look at that voltage supply. Neither side is connected to ground. And this is our special case that gets called Super. I always wanted to have a costume, like Superman costume, when I teach this, but no such luck. I should go raid the kids' toys and see if I can make Superman fly through the thing. Anyhow, all right, so we started out the same way, but we've got to recognize that we've got a voltage supply, and that's going to cause us to write a KVL just like it did in the last problem. Okay, so I'm looking at this and I'm going to say we've got 4 unknowns and 1 voltage supply. So we're going to write 1 KVL and we've got to write 3 KCLs. That's going to give us the total of 4 unknowns, or 4 equations for our 4 unknowns. We can go ahead and solve that system. All right. Let's see. Where do we want to dive in? So if I see the voltage supply, let's go ahead and write that one. So let's say this is the KVL for the... Oh, this has a name. It's called Super. I said that, and then I didn't finish it off here. Okay, so this is what we call a super node. We had super loops with mesh. We have super nodes with nodal. Okay. And this is going to be created by a voltage supply connected to 2 non-reference nodes. Connected to 2 non-reference nodes. All right, and that's what we see here. That 8-volt supply is connected to B and C. Neither side is connected to ground. Okay, so let's write that one for starters. So let's write the KVL for the super node. All right, a lot of times what I do is I box this up and I go, okay, in here, those 2 nodes together, and that's form our super node, one big node. Okay, so let's see, what's connected to the positive side of the 8-volt, VB, what's connected to the negative side of the 8-volt, VC, and that's just equal to 8. That one's done. Ooh, I had been using blue. Right. There we go. All right. That one's done. So then we got 3 KCLs. And we got to look at where we write these KCLs. Right now, without more information, we can't write a KCL for any node that is connected to a voltage supply. Same problem with mesh, where we couldn't write a KVL for a loop that had a current supply in it. What we want to avoid for right now, let's go yellow, right? Avoid KCLs for nodes with voltage supplies attached. I'm not saying we can never do it, but when we're trying to find the node voltages, then we want to avoid them. Okay, so let me roll out of the way here. So what nodes are those? A looks okay. There's no voltage node, voltage supply connected to that. I can't write it for B because I won't be able to write this current in a way that involves the node voltages. Okay, So the same is true of C. It's got the same 8 volt attached to it. And I can write it for D. So A and D I'm good with, but that's only 2 KCLs. Okay, and we'll go write those in a moment. The third KCL comes from a bit of trickery that Kirchhoff pulled on us. And maybe I didn't state this way when I introduced Kirchhoff's current law. But the way he originally stated it was that the currents entering a bounded region of a circuit has to algebraically sum to 0. So that's why I drew this box around here. Here's our bounded region. All of the currents going into that bounded region and out of that bounded region have to be accounted for. But there's internal current that we don't have to worry about, okay? Because if it shuffles here, it's got to pop out over here somewhere. So it's going to be accounted for as long as we have this bounded region and we say, okay, I have this current, this current, this current, and this current connecting to that supernode, and the supernode is that bounded region. So I'm going to write the KCL for that supernode, and I'm going to have 4 terms involved in it. Let's see if I have enough room down here. Let's say KCL for the supernode. Okay, VA minus VB over 6 minus VB over 12, right? And I'm dropping that 0 now, minus VC. If you're not comfortable with that, go back and watch the previous videos where I talk about it. Minus VC over 4, minus VC minus VD over 8. And that's equal to 0. Okay, there's our KCL. That's a perfect KCL. Nothing wrong with it. I said perfect KCL, and then I'm like, oh, I better check it. I think it's good. We got to do a little bit of algebra to it. But at this point, it's just kind of the same algebra we've been doing with the other ones, so it's not a big deal. 1/6 VA plus minus 1/6 minus 1/12 VB plus minus 1/4 minus 1/8 VC plus 1/8 VD, and that's equal to 0. Okay, so I did that pretty quick. Totally double check me. Let me know if I screwed it up, but I don't think I did. I'm feeling pretty confident about it. That's usually when I make mistakes, is when I'm feeling pretty confident about things. Anyhow, okay. So we got to reduce some fractions, of course. 1/6 VA. This is going to be minus 3/12, so that's going to be minus 1/4 VB. We got minus over here as well, and it's going to be minus 3/8 VC plus 1/8 VD, and that's equal to 0. All right, that one's ready for prime time. Okay, so those are kind of the two equations that are a little bit different. This is a KVL, and then this is a KCL, but it's a KCL for a bounded region, and this is the first time we're doing that. So, but it's still a KCL. It's a sum of currents, right? This is a voltage, this is a resistance. That term is a current. Make sure all of your terms are currents when you're writing a KCL. Checking the units goes a long way. All right, what's left here? We've got 2 KCLs. We got a KCL for A, and we've got a KCL for D. So let's scroll down here. Go ahead and open the image if you can, because all the scrolling is going to get a little difficult. And I think these are similar enough to what we've done in past videos that nothing should shock you with this. That's an electrical pun. And I'm just going to make sure I have my... Yep, I did my down and right thing so that I write it consistent with what's up there. Okay, so KCL for A, it's going to be leaving, and it's going to be VA minus 0 over 3. And then the current through R2 is also leaving, and it's going to be VA minus VB over 6. Okay, and that's all of my currents for that one, so it's equal to 0. So we got a negative 1/3, negative 1/6 in front of VA, plus 1/6 in front of VB, and that's equal to 0. So let's see, we've got a third and a sixth, so that's going to be negative 1/2 in front of VA, plus 1/6 in front of VB, and it's equal to 0. Okay, that one's ready to go. All right. We got the same thing for the D node, so this is the KCL for D. This current is going to go in, and it's VC minus VD over 8. And the current through R6 is leaving, and it's going to be VD minus 0 over 5. Ooh, that one's going to get funky, and that's equal to 0. Okay, so 1/8 in front of VC, minus 1/8, and minus 1/5 in front of VD, and that's equal to 0. Just do that little bit of arithmetic to find that we have negative 13/40 in front of VD, and that's equal to 0. Okay, so there are my 4 equations. Let's organize these a bit so that we can get the matrix set up nicely. There's one of them, and then let's grab this one as well. Okay, and how much paper do I have left? Yeah, good. Okay. And this one's going to be 4x4. Oh, gosh. We'll survive, I promise. Okay, negative 1/2, 1/6, 0, 0. Invert it. Multiply by the right-hand side, which is also 0 in this case. All right. I'm moving over to this one over here, top right. 0 for VA, almost got you. 0 for VB, 1/8 for VC, and negative 13/40 for VD. Right hand side is 0. Okay. Bottom left over here, oh, here's our KVL. 0 because there is no VA, 1 because there is a VB, negative 1 for VC, 0 for VD, 8 on the right hand side. Last one, this monstrosity, 1/6, negative 1/4, negative 3/8, and 1/8. Okay, and that's 0. All right, doing that little bit of linear algebra, and we're going to get VA, VB, VC, and VD. Okay, grab your calculators, folks, and hold on tight. Here we go. Whoops, that was loud. Okay, it's a 4x4, negative 1/2, 1/6, 0, 0, 0, 0, 0, 1/8, negative 13 divided by 40. Sure, 0. 0, 1, negative 1, 0, 8. Who loves watching me use the calculator? Negative 1/4, negative 3 divided by 8, and 1/8, 0. And from that, oh yeah, these look familiar. You do the same problems every year. Every once in a while I go, yeah, those numbers look like I've seen them before. We get 1.67. I'm doing a bit of rounding. I don't have a specification I'm working to, so I'm not overly interested in getting the precision where it needs to be. We'll leave that for other classes for you. 5.0, oh, that should really be 2. Let me grab an eraser here, and I don't like that 5. 5.02 volts. Negative 2.98. volts and negative 1.15 volts. All right, there are our node voltages. That's good. That's a start, right? I'm going to actually store those for safekeeping. We've got to use those. We've got to use them to find whatever it is we're looking for in this circuit. So let's go peek at the original circuit again. You're probably looking at the image, I hope. And we can see that we have I out here. So really the problem that we're trying to solve is find I out. And kind of implied we should be using nodal analysis. This might be where you go, why didn't I just use mesh? And that's true. I'm not coming to your job with you. You get to pick the method of analysis that you think is right for the job. Make sure you can get it right. Okay. But right now we want to find this current, and here's what's special about this current. It's through a current. It's through a voltage supply. Okay. And I said that we had to avoid writing a KCL when we're trying to find the node voltages. Avoid writing a KCL that's for a node that has a voltage supply connected to it. Oh, I have it right down here. Look at that. It's right behind my head. Okay. And that's because when you do that, you add an unknown. And then you're just going to need another equation anyways. So we're going to go write another equation, but we're going to have one equation and one unknown because now we know VA, VB, and VC. So you can pick a node that has that current going in or out of it. And I'm going to pick VB just because it's on the left and I'm being quite lazy. So I've got 1, 2, 3 currents that I have to account for, and one of them is unknown, I out. So if I wanted to find the current through a passive component, we can just use voltage at the tail minus voltage at the tip over the resistance. But here's a case where I have the current going through an active element, and it's not a current supply, so it's through a voltage supply. We got to do something a little different. We've got to write another KCL, and I'm going to write this KCL for B. So I'm going to have VA minus VB over 6 minus VB over 12 minus I out. That's all 3, so that's equal to 0. Then I can plug in some values, and I can solve for I out. So let me go write that down below, and I'm going to open up my notes so I can see the circuit again. Okay, so now to find I out, I'm writing the KCL for B, which before was not allowed. Well, I mean, you can do it, but you're adding an unknown and doing it. So this is going to be VA minus VB over 6 minus VB over 12 minus I out equals 0. Okay, the only unknown is here. Oops. And then we just got to plug some stuff in. So we've got 1.67 minus 5.02 over 6, and we've got minus 5.02 over 12, and I can bring that I out over to the right hand side to get it all by itself. Okay, and then we can just calculate it. So I'm grabbing my calculator again. That's why I stored the values. If you don't know how to store values in your calculator to reuse them, it's pretty useful because that's what I'm going to do here. Okay, so let's see, that's VA minus VB divided by 6 minus VB divided by 12. Okay, and from that, let me just check myself. Past Dave calculated this. That guy's doing me a solid right here. Okay, our node voltages match up. That's cool. And our current matches up. That's great. Okay, so we get negative 975.4 milliamps. And there's our answer. Okay, so new special case. We got a supernode for the first time. And that wasn't the only thing special about this problem. We had to find the current through a voltage supply. And to do that, we had to write one additional equation. We had to write a KCL. So you will run into problems like this. And we're still using the fundamental laws. KVL, KCL, Ohm's law. Okay. I think I have some more examples of supernodes just so that you get comfortable with them. And then we get to do some dependent supplies after that. All right. Stay tuned and good luck.